In this video, we're going to start talking about sequences. Okay, so we're going to start with defining what a sequence is. Okay, so a sequence is a function whose domain is the set of positive integers Okay, so what that means is the inputs, the inputs of your function of a sequence are, so they start at 1, 2, 3, okay, but they're just the integers. So you don't want to write like x bigger than 1, bigger than or equal to 1, because that includes all the real numbers, okay, so we only want integers here. We tend to think of sequences as lists of numbers that have some sort of pattern. Okay, so let's do an example. So let's say we're given a sequence defined by b sub n is 1 over 3 all to the power n. Okay, so what's going on here, this thing here is the equation that gives each term in the sequence. Okay, so if we wanted to find B3, okay, then this is the n value is 3. Okay, so B3 then is going to be 1 over 3 to the power 3, because the n is 3. So that's 1 cubed over 3 cubed is going to be 1 over 27. Okay, so similarly, B5 is going to be 1 over 3 to the power 5, because here the n value is 5. So that is going to be 1 over 243. Okay, so what this sequence would look like, so the sequence would be, so it start with n equals 1, okay, so that's going to be 1/3, and then we have n equals 2, so that's 1 over 9, and then n equals 3, 1 over 27, n equals 4, 1 over 81, etc. Okay, and then it keeps going like that. So that's how we would write the sequence if you don't write it in this sort of closed form. Okay, let's try another one. So I'm going to skip the C one. Okay, so we'll leave a blank for it. And we'll do the D one. Okay, so we want to find the first 5 terms of the sequence. Okay, and I'm going to use the Dn. So this is giving me the formula for each one. Okay, so D1. Okay, this is, so n equals 1, so it's odd. Okay, so if n is odd, then my term in the sequence is the number 1. Okay, so for D2, so here n is 2, so that's an even number. Okay, when it's an even number, we use n squared, so that's going to be 2 squared or 4. Okay, so for D3, n is odd, so it's the number 1. Okay, D4, n is even, so it's going to be 4 squared or 16. And D5 is odd, so this is a 1. Okay, so this is odd. Okay, even, odd. And then our sequence would be 1, 4, 1, 16, 1, etc. The pattern continues. Okay, now it's harder to find the pattern when it's not given. So if we had these sequences, we want to find a formula for the nth term. So this is going to be n equals 1, 2, 3, 4, 5. Okay, so you want to see a pattern. So you might notice that each of the numbers is double the input. Right? So it's going to be 2 times the input, but then they switch from from positive to negative, positive to negative, positive to negative. So all the even ones are negative. Okay, so if I want a formula for an, okay, what that's going to look like, so I'm definitely going to have 2 times n. Okay, and some of them are negative, so I'm going to have a times -1, and now I need the power on the -1. So there's different ways to write it. Okay, so when n is 1, I want the power to be even, because n equals 1 is positive. When n equals 2, I want the power to be odd. So I think if I put n plus 1, okay, then if n is 1, then I get 1 plus 1 is 2, so that's a positive number. And if n is 2, I'm going to have an odd number up here, so then the -1 is going to be a negative power, a negative number. Okay, so that's the formula for that sequence. Okay, I'm going to leave part B for you to try, find the pattern. And let's talk about a factorial. Okay, so the factorial symbol, so we call it n with an exclamation mark. So exclamation mark is the factorial symbol, okay, is defined by, okay, so 0 factorial is 1, okay, and 1 factorial is also 1. And then if you want n factorial for anything bigger than 1, what you do is you take n and you multiply it by all the integers that are less than it, okay, until you get to 1. Okay, now if you want, this part would be n minus 1 factorial, because I take n minus 1 and I multiply by all the integers that are less than that. So you could also write this as n times n minus 1 factorial. That's another way to write it. Okay, so they gave you some examples down here. So 4 factorial would be 4 times 3 times 2 times 1. Okay, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So you take this integer and you multiply it with every integer less than it until 1. Okay, there is a button on your calculator . Okay, it normally looks like that with a n factorial. And I believe it might be over the 4. Okay, so it's usually on the numbers portion. Okay, so over one of the numbers there. I think it might be the 4, but I'm not sure about that. Maybe I should just put a question mark. Okay, something like that. Okay, this is an example of a recursive sequence. Okay, so a recursive sequence is one in which the first term or the first few are defined explicitly, so they're given. But the remaining terms are defined using one or more of the previous terms. Okay, so that's what it means. Okay, so the factorial does this because we define n factorial in terms of n minus 1 factorial. Okay, so you can define n factorial by saying it's n times the factorial before. Okay, so that's a recursive sequence because I defined the term for n using the term for n minus 1. Okay, so that's the idea. So let's do an example. So here I have S1 is 1, so they gave me one term explicitly, And then they told me that Sn, so the nth term, is n times Sn minus 1. Okay, and we want the first 5 terms of this sequence. And a non-recursive definition, so formula. Okay, so S1, so let's just write out a few terms. S1 is 1. Okay, S2 is 2 times S1, so that's 2 times 1, or 2. Okay, S3 is 3 times S2, so that's going to be 3 times 2, or 6. S4 is 4 times S3. Okay, so that's 4 times 6, which is 24. Okay, now S5, is 5 times S4. So that's 5 times 24, which is 120. S6, this is the last one I'm going to do, so it's 6 times S5. So that's 6 times 120, so it is 720. Yeah. Okay, so those are the first few terms. Now a non-recursive, so we want a non-recursive formula. Okay, so how else could we write Sn? So the nth term. Now I did all the way to S6 so that maybe you might notice. But let's talk about this a bit. Okay, so instead of doing, when we did 3 times S2, I wrote 3 times 2. But I could have wrote 3 times how I computed S2. So this, from here, it could have actually been 3 times 2 times, 1. Right, if I didn't actually compute S2 first. Okay, same with this one. So then 4 times, and then S3 is 3 times 2 times 1. Okay, and then this one is 5 times S4, which we just did, is 4 times 3 times 2 times 1. And you might notice that I end up multiplying all the integers that are n or less. Okay, this is why I went to S6, because we computed these ones earlier in the examples. Okay, so for the factorial, 4 factorial is 24, and 6 factorial is 720. Okay, so then notice S6 was 720, S4 was 24. And it does look like we're doing the factorial for each one. Okay, so that would be our non-recursive formula. So then I don't need to compute the ones before. I can just use my calculator and say that, I don't want to do one that's too high, but let's say, so then S9 is 9 factorial, which is 362,880. Okay, I didn't need to compute S7 and S8 to get it because there's a button on my calculator. Okay, so that's why it's non-recursive, because it's not using the steps before. There's a way to compute it without that. Okay, this is the recursive definition for the factorial, and I did sort of mention, so it's n times the one for before, and it starts with 1. Okay, so that's how we can define the factorial. Okay, now this one is similar, but I'm going to leave it for you. You don't have to come up with a non-recursive formula because it's actually quite difficult. So this sequence is a very special sequence. So you won't know what this is, but I'll fill it in the next video. But it does tell you here, it has to do with something called the golden ratio. So the ratio of the terms is this special thing here. Okay, so the formula is not easy to come up with. So don't try. Just compute the first 5 terms. Okay, so something else that we use is called summation notation. So suppose we want to add the first n terms of a sequence. Okay, so the sequence is an. So what I want to do is a1 plus a2 plus a3, and I want to add until I get to an. Okay, there's a way that I can write that I want to do this, okay, and it uses what we call sum. So the notation is a capital sigma, okay, and then we write that we want to add a k, and I'm going to write k equals 1 to n. Okay, so let's explain these. So this means that we're going to start at k equals 1, and this thing up here means that we're going to end at k equals n. Okay, and then the ak is the formula giving the number to add to the sum. Okay, so the number, the number to add for each term. Okay, now here k is called the index of the sum. Okay, because as k changes, you plug in a different thing into this formula here, the thing inside the sum, and that tells you what term to add next. Okay, so this is read the sum of the terms ak as k ranges from 1 to n. Okay, so let's do an example. Okay, so here we start at k equals 1. Okay, we're going to end at k equals 5. Okay, and the formula, so ak is 1 over k. Okay, this is the formula for each term. Okay, so what this sum is, so we start with k equals 1. Okay, I'm just going to write these. So we're going to do k equals 1, and then we're going to add k equals 2, k equals 3, k equals 4, and k equals 5. Okay, so when k is 1, I plug in k equals 1 into the formula, and I get 1 over 1. When k equals 2, I'm going to have 1 over 2. K equals 3 is 1 over 3, etc. So k equals 4 is 1 over 4, and that is 1 over 5. If you add these together, you get 137 over 60, which is approximately 2.2833. Okay, so that's what the sum equals. Okay, but that's how you would compute it. Okay, now going the other way, if they give us a sum and we want to write it in summation notation, okay, so I'm just going to, so this part, so you can pick where you start, but because everything's cubed, I think it makes sense to start, this is k equals 1, 2, 3, and this will be 8. Okay, so those are your k values. So I think that this sum, I'm just going to write equals. So it's going to be the sum. So that's what that notation means. So we're going to start at k equals 1 and go to the number 8. And for each term, so if you look at this term, it's k cubed. Okay, this term is k cubed if k is 2. This term is k cubed if k is 3. So that's our formula. Oops. So our formula is going to be k cubed. Okay, so that's how we could write that in summation notation. Okay, I'm going to skip number 8 and let you try. Okay, some properties of sums. So if you have an and bn are sequences and c is some real number, so if you want to compute the sum of a constant times a sequence, you can actually pull the constant out. Okay, so the little proof for that. So if I have from k equals 1 to n, c, a, k, what that's going to look like is C times A1 plus C times A2 all the way to C times AN. And then notice I can factor out the C from all of those. Okay, and then this part, okay, is a sum. So this is actually C times the sum of the A's. Okay, so that's why those things are equal. Okay, now if I want the sum of two sequences added together, okay, I can do them separately and add after. Okay, so a little proof for that. Okay, so this would be, if I just write it out, it's going to be A1 plus B1. And then I'm going to have A2 plus B2. And I'm going to do that until I get to AN plus BN. Okay, but these things are all adding, so it doesn't matter what order I add. So I could instead add all the A's, and then add all the B's. Okay, which is the same as doing the sum of the A's and then adding the sum of the B's. Okay, so you see that's why that works. It's the same for minus. I'm not going to prove this one. Okay, I am going to put these in little boxes though, so we can use these just so they're a bit easier to see in the notes. Okay, so this proof is the same as the one above. So here you can split up the sum. So here it's going from k equals m to n. So we could go from 1 to n, if that is easier, and then subtract these are the terms that we don't want. Okay, so this is... So those are going to be the terms. So we take up more terms than we need and then subtract off of the ones that we don't want. Okay, that's another one. So maybe I'll try to explain that. So the sum from k equals m to n of ak equals the sum of the terms from am to an. Okay, so what we could do instead, take all terms from A1 to AN and then subtract the ones that we don't want. So that's A1 to AM minus 1, because I do want AM. Okay, so that's sort of what's going on there. Okay, so some easy ones to compute, or some ones that we often see. Okay, so if you have the sum of a constant, okay, there's no k to plug in. So for k equals 1, it's just c. For k equals 2, it's just c. For each term, it's just c. And then we want to think, okay, how many terms are there? Well, there's going to be n terms because we're going from 1 to n. So that's going to be c times n. Okay, now if you want to do the sum from 1 to n of k, so you're doing 1 plus 2 plus 3 all the way up to n. Okay, there's a formula for this. It's n times n plus 1 all over 2. Now I can sort of try to tell you, I'll try to explain this one. So you could think about it as adding up some boxes. Oops, that's too big, but okay, whatever. So I'm just going to keep going here. So let's say that this is what we want to add up. So this is 1, 2, 3, 4, 5, 6, 7 boxes, right? If we do the exact same thing on the other side, but going backwards, so I put an okay, so it looks like this. Oh, I'm messing this up here. That should go like that. Okay, so like that. So here again, I have 1, 2, 3, 4, 5, 6, 7. So I'm adding the same number of things. Okay, so this is like my n. So my n would be 7 here. So this side has length n, and this side has length n plus 1. Okay, so the area is going to be n times n plus 1. So that's the number of all of these boxes, but we only wanted half of them. So that's why we divide by 2. Okay, so this is proof by picture. Okay, so that's sort of why that works. I'm not going to explain the others. But so k squared from 1 to n, that's 1 squared plus 2 squared plus 3 squared, etc. to n squared. That one looks like n times n plus 1 times 2n plus 1 over 6. Okay, k cubed, so that's 1 cubed plus 2 cubed all the way to n cubed. That one you can do as n plus 1 over 2 all squared, or you could write it n squared, n plus 1 squared over 4. Okay, now these, normally we have a formula sheet in this class, so these ones are all given on the formula sheet. Well, the last 3 anyway. Okay, now we can use these to find some sums. I'm going to leave the hardest one for you to try. Okay, so the sum from k equals 1 to 7 of the number 4, so this is 4 plus 4 plus 4, okay, plus 4. So this is k equals 1, k equals 2, k equals 3. This is going to be k equals 7. So that's going to be 7 times. Okay, so it's going to be 7 times 4, or 28. Okay, using the formula above. Now if I have 5, the sum from k equals 1 of 5k, I can actually take out the 5. So it's the sum from 1 to 8 of k, using the constant multiple rule. Okay, and now I can compute this sum. So here my n is 8, and the formula is just k, right? So that's like this one here. Okay, so I can use this formula. So this thing is going to be 5 times, so it's 8 times 8 plus 1 over 2. So that's going to be 5 times 36, which is 180. Okay, so that's how you could compute those sums. And again, I'm going to leave this last one for you, but what you want to do is break it apart and then compute each of the sums. So you're going to have a sum of k's and a sum of k squareds and a sum of constants, and you can compute each of those using the formula.